This is the last chapter of the course, which is exciting for every student. But also I found a lot of students find this interesting. They wonder just what is nuclear chemistry. Let's get started. Nuclear chemistry, it is different. When we had regular chemistry, we were making or breaking chemical bonds. We never had an atom change. When we talk about a nuclear reaction, we are going to be doing a transformation. You may be getting an isotope, or you may be getting a brand new element. So if someone says an element is radioactive, many of you already know that uranium is radioactive. It is something where the nuclei will spontaneously change, and it goes from a 238 to a 235, and it also emits radiation. So the field of nuclear chemistry, what it does is it looks at nuclear reactions. OSU has a one-semester course in engineering. A lot of my students have taken it, primarily from interest, but if they're going into medicine or maybe they're going into something in the nuclear industry, it's part of what they actually in the beginning, we're learning it, okay? So section 21.1, I've summarized every single table in this section on the first slide. Let's to the B had a slide that had what are the particles you have in the reactions, and there they sit. What are their properties? I'd say don't have to go that deep. I mean, we really are 1220. And an example of all the different radioactive decays. If you're able to add the atomic masses, add the atomic numbers, you will be fine in this section. Explain it. When we talk about a nuclear process, we always have a symbol that looks like this. The E stands for the element. The A is the number of protons and neutrons, and the Z is the atomic number. So let's take something you knew about really well in Chemistry 1210. We would talk about carbon. We would say 6 protons, 6 electrons, and 6 neutrons. We never went past that, but elements have isotopes. If we had carbon 13, it still had 6 protons, it had 6 electrons, but now it had 7 neutrons. It is not radioactive, but it is an isotope. So let's talk about isotopes that are radioactive. One of them, well, we'll talk about this one, is uranium. 238 is its atomic mass, 92 is its atomic number. So it has 92 protons, 92 electrons, and 238 minus 92, which says we have 146 neutrons, if I did my math right. So this is the starting point. We want you to understand that it is up. We're looking at protons, electrons, and neutrons. Notice for uranium, uranium-238, it is the most prevalent isotope. That goes back to 1210. Uranium-235, that is the one that people use for power plants and sadly to make bombs. So again, lots of information here, but the whole idea is understand what a nucleide symbol is. If someone uses the word radionuclides, they are talking about all sorts of nuclei that are radioactive. If they talk about a radioisotope, that is an atom containing radionuclides. So again, language, but the most important thing is, can you figure out the number of protons, electrons, and neutrons, and do you know what an isotope is? Atoms with the same atomic numbers, but a different mass number. So we've got a number of particles, and each slide shows one. An alpha particle is signified by the Greek letter alpha, and people often talk about alpha decay. So an alpha particle is a helium nuclei. We talked about that back in chapter 2 in 1210. Uranium-238, it emits an alpha particle, and you can see there is the helium. What I want to point out is how we balance. If I take the atomic mass of uranium, and if I look at the atomic mass of thorium and the atomic mass of helium, you will see that the numbers have to add up. That's what's in the box, balancing equations for nuclear reactions. The masses must add up, and the atomic numbers must. 92 is the atomic number of uranium, if I look at the atomic number of thorium and the number for helium, you can see that 92 equals 92. So this is really easy, best way to put it. So here's a typical problem. It says that palladium-210 undergoes an alpha emission, which is a helium particle. What is the product nucleus? So I would look and I would say, well, 210 has to equal some number plus 4. I would also say 84 has to equal some number plus 2. Well, I would look at the atomic number first because that is going to set the nucleus. The question mark here is the number 82, and 82 corresponds to lead. You'd look at the periodic table. So that's part of the problem. Now, if I know it is lead, I have figured that out. What is the second question mark equal to? Well, 210 minus 4 is 206, and that will be the atomic mass number. So the answer to this question is PB 206 with the atomic number 82. Remember, this sets the element. It is that simple and a joy after what we've been backwards. There's another sort of particle called a beta particle. It is symbolized either as a 0e minus 1, I'll put it here, or sometimes they write it in this manner. But most likely it's going to be symbolized that way as a beta particle. Since it has a superscript of 0, it says an extremely small mass for chemistry 1220. If it has a subscript of minus 1, it says that it has a negative charge, which is the opposite of a positive charge, which is a proton, not a photon, okay? If there aren't any electrons in the nucleus, how can they come out? Well, just like when you strike a match, it has sparks, an electron comes out only when the nucleus undergoes a nuclear reaction. So what we have here, they look kind of confusing, but I'm going to look at first the atomic masses. 1 equals 1 plus 0. Then I'm going to say here's a 0 and a 1 and a minus 1. And what we have is 0 is a 1 minus 1. Now you do not have to go deep here. What you just need to know is what is a beta particle, what is its symbol, and if someone gives you a reaction, a nuclear reaction, you know that the atomic mass numbers must equal on both sides of the equation. And you know that the atomic numbers must equal on both sides of the equation. It's very, very, very simple math. So again, do not make it too complicated. Our third kind of particle is a gamma ray, and that's gamma radiation. Think back to chapter 6. Electromagnetic radiation that has a very short wavelength, about 10 to the minus 12 meters. How do we represent it? We represent it with that symbol. And often it is never shown in a nuclear equation. The last section of this chapter talks about how alpha, beta, and gamma rays affect human beings. So you'll just have to hang on to that. The last slide of this section talks about two other types of particles. One is called a positron, and it's used when people do transmutations. There are some examples. I'll let you go through them by yourself. The other one is called electron capture, and it'll be talked about in the next section also. So we're